So thank you all for staying until the very last talk. So this second part of my talk is about the topic which is related to distributed optimization, but it's called slightly different. It's called distributed learning. So hopefully by the end of the talk you will understand what is the problem of distributed learning and what do I mean by cooperative inference. This is joint work with my former advisor Alex Olszewski and Angelia Nedic. So first of all is the real meaning of these words, which is distributed. We already understood what is distributed. Learning, of course, is optimization. Cooperative is consensus-based, and inference is the statistical estimation. So this talk is really about distributed optimization for consensus-based statistical estimation. So next. So this is, I guess we are all familiar with random variables. So this is going to be a different talk, more on the statistical side of the problem. So this is by definition, when you are trying to solve some estimation problem, there is three main components that you need to take into account. The first one is called the data, which is a random variable which is distributed according to some probability distribution that I call P star. So capital X is a random variable, and then some sample space. The thing is, because this is data, we don't know P star. This data comes from physical process, from measurements, so we don't know exactly what's the distribution, but we assume it's a random variable and that this distribution exists. Second component is a model. And what is a model? It's a collection P of probability measures. So it's, let's say, a set of many different probability measures.
So for example, it can be a parametric.
For example, a family of Gaussians, and then and this family is going to be parameterized by theta.
Okay.
So theta is the parameter of this family. And this is the important part. So there exists an injective map between the parameter space and the family of probability distributions. That means that I can give you a theta, and once you give me a theta, I can find a member on the family such that p theta, so that theta generates p theta. Right? So only one, yes. So for example, I can say my family of distributions is Gaussians and my parameter is the mean. So given a mean, I can generate a Gaussian with parameter theta. That's and this is just for technicality. I'm going to assume that all the probability distributions inside this family are dominated. That is, there exists lambda, which is a probability measure, such that all these p theta are strongly dominated by lambda. And what that means is that if distribution is positive, then lambda is also positive, right? But this is a technicality. And just for notation, so capital X I'm going to call random variables. Lowercase are going to be realizations of this random variable. And capital P is probability distributions, and lowercase p are densities. So the density of the corresponding probability distribution. So this is the definition here. And the third part of the estimation problem is an estimator itself. And what is it? It's a map that goes from the input space, so sample space of the random variable, into the family. So it's a function that you input data and outputs a member of the family. So an estimator is just a function such that you put the data points and the output is an approximation, or what's a member of the family, right? So, and ideally, we would like to have our estimator such that is the best guess of p hat inside the family that is the closest to p star. That is going to be the problem, right? So we have, based on the data, we generate an output that I call p hat, and ideally it will be the closest to p star. Remember, p star is unknown. So you can imagine, again, the example with Gaussians. So we are trying to, let's say X is Gaussian with unknown mean. My family is the family of Gaussians with unknown mean. And my estimator is, for example, empirical mean. So the output is a Gaussian with mean at the empirical point, and ideally, this Gaussian with mean and empirical mean is going to be the closest to the Gaussian with the actual mean of the data points. Right?
Excuse me, one question. What is a sample space? Why are there two X?
Oh, because one is the space where the realizations are coming from, and second one is the sigma algebra.
And the last formula on the previous slide was
right.
Like maximum likelihood.
Yeah. For example, one of them is maximum likelihood estimators, but there is many other ones. Yeah.
Yes. What is lambda? It's some number.
No, lambda you can consider, for example, any like I forgot the word, like. You know, like uniform distribution, for example, is just the measure that you use to define the density, right? So the definition of a density itself is like the Nikodym derivative. So you need to find some lambda for that. But in this case, like for example, the Lebesgue measure is one of them that you can use. So, but this is not important. This is just technicality. Lambda will never show again in the talk. So now we understand what's the problem of estimation. So now I'm going to introduce what's some formality about Bayesian methods. So the understanding with Bayesian methods is that now my parameter, remember the theta parameter in the previous slide, is now a random variable. And I will call this like fancy theta. And also that takes values in a different sample space. So this is realizations are in theta, but then now I have also sigma algebra over there. And ideally, so there is a probability measure on the space of samples and parameters with the corresponding sigma algebra, which is just the product, such that maps members of the sigma algebra to the points between 0 and 1. And the model itself is the distribution of X conditioned on theta. So my model is what is the distribution of X of my observations, given that the parameter where they came from is theta. Right? So this is a a conditional distribution of two random variables. The prior, of course, is the marginal of theta with respect of pi, of this distribution pi, with respect to one of the parameters. And the posterior is the probability of some theta given some observations b. The posterior is the probability of theta being in some subset b given some observations, and this is just the ratio between this measure over b over the measure of the complete set. This is just let's say Bayes' theorem. I can ignore this. So now I'm introducing belief notation, which is going to be all around the talk. So this is very important. So what I'm going to now define is this measure mu, which I will call beliefs, which is the probability distribution of some theta. So b mu sub k of theta is the density of the probability distribution of theta given some observations up to time k. That is going to be my belief. And because these x's, I'm going to assume they're independent, so these things factorizes. So I have this recursion, which is just Bayes' theorem, right? My beliefs on a hypothesis theta or on a parameter theta is equal to the likelihood of the observation at time k given theta times the beliefs at time k minus 1. So this is just some recursion, right? Then this defines this algorithm. It's just bias. Posterior is proportional to prior times likelihood. This is just a very complicated formulation of Bayes' theorem, but this is just formality. And now this is important, which is the first time I define what is learning. This is the difference between like machine learning and statistical learning is that now we have proper definition of learning, which is the following. So given my beliefs, my density of beliefs here, I will say we learn the parameter theta star if this distribution concentrates around theta star, almost surely, right? So remember, mu is a probability distributions over the parameter space. I will say I learn a parameter if this probability distribution concentrates around one value. And then I say I learned that value. That's the definition of learning. Yeah.
Do I get it right that you assume that your data comes from some parametric distribution?
Not exactly. I assume my family is a parametric distribution. And I try to find the closest member of this family to the actual distribution. So let's say P star might not be inside the set of the parameter space. Right? What I'm saying is there might not be a theta such that P of theta is equal to P star. Right? But it's the closest. So we hope that P of theta star is the closest to P star.
So it's kind of similar to variational approximation.
Yeah, in a sense, yes. Yeah.
Excuse me, but why the multiple of P theta of xi equals to the, well, yes, the last equality.
Yes. Okay. So you what is recursion? So you can take one out. So take the k term out. So you have product from I to k minus 1 times this theta, and that's the definition of d mu k minus 1.
So what is the meaning of mu k? It's a probability measure.
It's a probability measure over the parameter space.
Okay.
Right? So it's yeah, and that's precisely what we define learning is. Let's say we start with uniform distribution, which is we don't know exactly which parameter are we working on. And as we're getting more data, we are concentrating around one particular parameter. So we are learning that parameter, right? And then, for example, of course, the Gaussian case. So now the data. So what I'm going to do now is I'm going to talk about these three things for the Gaussian case. Yeah. So the data. So assume we're receiving samples like from 1 to k. And these samples comes from a random variable, a Gaussian, with some mean, theta star, that we want to estimate, and some known standard deviation. So the problem here is we want to estimate the mean. Right? What is the model? So the model will be the collection of all normal distributions with variance sigma star. Right? This P of theta is all the Gaussians with parameter theta. What is the prior? So let's assume, for example, our prior is the standard normal distribution, which is so our beliefs about the parameters are just the Gaussian with meaning 0 and standard deviation 1, for example. That's another case. And you can do computation, and then the posterior, let's say the beliefs at time k is just going to be the product of the density of the Gaussian here times the product of these likelihoods, and these likelihoods are also Gaussian. So because these are conjugate priors, the beliefs at time k is a Gaussian random variable with this mean and this standard deviation. So the mean is just the empirical mean. You see, this is average of xkt. This is just empirical mean, and standard deviation is something that decays as k goes to infinity, right? So what's going to happen here? This is the easy case that we can analyze by just watching it. So as k goes to infinity, let's say as I get more and more data, the beliefs, the standard deviation of the beliefs are going to go to 0, right? So what that means is I have a Gaussian is going to like thinner and thinner and thinner. And the mean of this Gaussian variable is what is going to happen. So what happens when you take limit of as k goes to infinity of this number? They're going to converge to expected value of the random variable. So what's going to happen is that the limit as k goes to infinity of this part here is precisely theta star. So what this is showing is the beliefs, so mu, which is a distribution over the parameter space, at time 0 is this number here, is this distribution here. And as k goes to infinity, is going to become a delta distribution over theta star, on theta star. So at that point, we say we learn the parameter that we want to estimate. Right?
Excuse me again.
Yeah?
As k goes to infinity, what's going on with our mean in yours?
Right here. So maybe I can. Yeah, here. So we know, if we have x. I have a random variable that is this Gaussian. I have the by central limit theorem. I have lim of 1 over k x I equals 1 up to k is equal to expected value of x. And by definition, expected value of k is theta star. Right? So our mean is going to go to theta star and our variance is going to go to 0. So I think I have a picture now. Yeah. So these are our beliefs. This is mu. This is our parameter space. We start from theta 0 at time 0. And this, let's say this is theta star. So as we get more and more data, say one data point. Another data point, another data point. See, this is the process that is happening. So a standard deviation is going to 0 and the mean is going to concentrate around theta star. Yeah.
So this probability measure of theta almost surely converges to the delta distribution.
Yes, correct, yes. And that's what we call learning. So we learn theta star. We learn a parameter that we wanted to from data. Okay, and this is another picture. So this is variance. So variance is going to 0. And the mean is also converging to some value theta star. So the interesting thing here is this picture. You know who this guy is, right? Yeah. Come on, you're Russians. You should know.
I think this is not the most famous
Okay.
picture from probably.
Oh, okay. Yeah.
Yeah.
Yeah. So the main, they say the main novel result, like 2-3 years ago of this paper was that I can show that Bayes' theorem is just one specific case of a stochastic approximation. Right? So that's the new result. So basically, all the theory for Bayesian analysis and statistical, all that, can be explained as stochastic approximation. Right? And we know, let's say, we as optimization people, we feel more comfortable on this side than on the other side. So basically, it gives us two. In particular, we are used to convergence rates, and statisticians, they are always asymptotic. So by having this understanding, we can provide non-asymptotic rates, convergence rates for statistical procedures. So that's the new result here. And also later I'm going to talk about the consensus-based and distributed scenarios and all that.
Is it the result that you mentioned? Is it the paper that is called like stochastic SGD as approximate Bayesian inference? Or probably It's a reverse one. Well,
No, this is called fast convergence rates for cooperative learning. Yeah. No, this is by me. So now let's explain what's the from the optimization perspective. So I guess this is going to be interesting for you here. So now let's consider this optimization problem. So it's minimization of a function over this parameter space, but now my function is Kullbaum-Leibler divergence. You know Kullbaum-Leibler divergence, okay? And between P, which is going to be P of P star, so the true distribution of my observations, and members of my family. So I'm going to find a parameter theta that minimizes the Kullbaum-Leibler divergence between a member of my family and the true distribution of the data.
So P here is
P star, yeah, I think it's the typo here, P star, yeah. So I just want to find what is the parameter that generates a distribution that is the closest to P star.
Probably a very annoying question that always arises in such situations. Why do you choose the Kullbaum-Leibler?
Because it works. It works so good. Yeah, it works very good. Yeah. So the first step is the following, and this is very interesting here. So we have optimization problem here over the parameter space. So now we are going to move from simple problem to a more complicated problem, but it's going to become easier later. So now look what I did here is I take expectation over a random variable pi, and I assume theta is distributed according to pi. And then I do minimization over the set of all probability distributions pi. You see what these two problems are equivalent? Because the solution to this optimization problem, let's say, is theta star. And then the solution to this optimization problem is a probability distribution pi that is delta function on theta star. And when I take expectation with respect to delta function, then I go back to original problem.
So delta theta is a space of probability distributions
over theta. Over theta, yeah.
Over theta.
Yeah.
So it's like a prior.
Yeah, so for example, imagine capital theta is all means between 0 and 1. So now delta theta will be all probability distributions over the set 0, 1. So before, the solution to our optimization problem was a point theta star. Now it's a distribution, but it's delta distribution over theta star. And when you take expectation with respect to delta distribution, then you go back to the original problem. Right? Okay, so now I've written the original problem as an expectation. And second step, I'm going to write Kullbaum-Leibler divergence as an expectation as well. And this is nothing new. You can always write Kullbaum-Leibler as an expectation. Right? And basically, Kullbaum-Leibler between P and P theta is the expected value with respect to P of the log likelihood ratio between P theta and P theta star. Right, so this is what we have here. So second step, now that we have two expectations, is the dominated convergence theorem, which means that we can exchange these two expectations. I can put the xp outside and a expectation of pi inside. That's what I did here. And what is even more important here is that the next step is showing that the solution to this problem is precisely the same solution to the other problem. It's just that here is a point and here is the delta distribution. So first I applied Kullbaum-Leibler divergence, right? And then I write the next step here. So next, what I did is the following. Look that d of p does not depend on theta, right? So it does not affect the arc mean. So it's only log of p of theta, so log of the numerator here. of random variable x, and x is distributed according to p, and theta is distributed according to pi. Next step, I switch these two expectations. And this is what I did here. Finally, now, okay, so now what I have here is now optimization problem with respect to an expectation of p. And let's consider everything here inside as of our function, the expected value with respect to pi as our function. So now how can we solve this using, let's say, distributed a stochastic approximation? So in a stochastic approximation, we start with an optimization problem defined as an expectation, just like this. And we can apply, for example, the stochastic mirror descent. And what is a stochastic mirror descent problem? Which is next iteration, so xk plus 1, is the solution of this problem, which is the linear approximation of our function with one sample of this random variable, right? So this is our random variable here, so here I just have one of the samples. And here I have to pick a Bregman divergence. And you can guess which one are we going to pick. The Kullbaum-Leibler, right? So now this is just a recall how we solve problems with stochastic approximation, with stochastic mirror descent. So now let's recall original problem that we have. We want to minimize this expectation, that's going to be the same one, of this function. So let's see how this algorithm looks for this problem, like specific version of this problem.
Do you keep track that you don't just use like HGG because you want this like Bregman divergence?
And also because we have a constraint here, right? So it's yeah. And I'm interested in mirror descent in particular because it's going to have a very nice function in the next slide. You will see this, it's like magic. So now let's write this algorithm for this function, right? So what we have here is realization of the expectation, right, of this random variable with respect to this expectation. So what we're going to have here is this function evaluated at one realization of this random variable with respect to p. So this is x, right? So it's minus logarithm of pt of x, and I've written this expectation with respect to pi as this inner product. Right? You see that expectation is the same as this inner product. And here minus log of x, now I have only one sample coming from p here.
So this double expectation is
it's only one expectation. One expectation because the expectation with respect to p, I have written it as this inner product.
Mm-hmm. Right. Okay. And the capital F is just the minus logarithm.
Minus logarithm, yes.
F is minus logarithm. Okay. And small x is what?
Small x is the realization of this random variable. So here we have random variable. Here we have one sample from that random variable. Here a random variable is capital X. Now we have one sample from capital X.
How do you take like the gradient?
Oh, because this is a linear function, right? Because here is a gradient with respect to x. So here is a gradient with respect to theta. And this is a linear function, right? Because this is an expectation, it's a linear function, so we got exactly the same.
Mm-hmm. What is the inner product of pi on the logarithm? Logarithm is the scalar, and pi is not. I don't understand.
Because, so first, so maybe I can write it as well. So first of all, we can write this expectation with respect to pi as inner product of minus log p theta x and pi, right? You see, this is a probability distribution and this is a value, so this is expectation, right? Mm-hmm. Just by definition, this will be the integral of this thing, right? And this is linear function with respect to pi. So gradient of linear function is going to be just this. So gradient, which is just this part, comma x, and x here is pi. So it's comma pi. So we got the same.
Okay, so you minimize all the space of probability distribution.
Mm-hmm.
This gradient is with respect
to this. Yes, correct, yeah. And the next step, so this is what we have here, and the next step, of course, is going to be, okay, I'm going to see distance, this is the distance between the optimization variable and the previous iteration, so this is distance between the optimization variable and the previous belief. So what I did here is I just written stochastic mirror descent for this optimization problem of double expectation. So next is the most important part, which is now a stochastic mirror descent means that we need to solve this optimization problem at each iteration. And let's see what happens. So it turns out that, I've just written it here again. This optimization problem, when you pick B to be the Cooperative divergence, has closed form solution. Right? So you don't need to use anything to minimize it because it has closed form solution. And what is this closed form solution? It's just Bayes method. Right? It's almost like unbelievable. So what we did is we start from a different problem, Cooperative divergence, and we apply the stochastic approximation algorithm, and it turns out that this algorithm is Bayesian posterior. So what this means is that what Bayes is doing is just computing next iteration of stochastic mirror descent. Right? So yeah, so that's an interesting thing, right? But now we have understanding of Bayesian posterior based on optimization, right? And of course, so I work with distributed optimization. So the natural question is, what is the distributed version of Bayes' theorem, right? And then because I know how to turn centralized problem into distributed optimization problem, now I have a Bayesian problem representation as an optimization problem. Now I can turn it into distributed optimization and see what is the distributed version of Bayes' theorem. Right? So that's going to be the next part. So now let's enter the distributed setup. So now we have a network. I think we already learned about this. So we have a network of agents. They're connected over a graph. So what's the distributed optimization problem? So this is the formulation. So now I have n agents from 1 to n. Each agent is observing a different random variable. Right? This is subindex I is the random variable that is observing agent I. And this random variable is distributed to some pi. So this is p star, but now because I have different one from each agent, so each agent is observing different random variable. And also now each agent has model. So same situation, but now it's for each agent. So each agent has a family of distributions parameterized by theta. Each agent has beliefs. So this is the notation D sub k is the belief of agent I about parameter theta at time k. And now we have an additional thing, which is in the same way that consensus you share your estimates, your current iteration. Now we allowed for agents to exchange their beliefs over the graph. So I'm going to send you the probability distribution that I currently have about the parameter space. And see what happens. And these are, of course, the weights that we always have. It's just the matrix A, right? So now, in the same way that we turn distributed optimization, we move from minimization of f to minimization of sum of f. So now the distributed estimation problem is we're going to minimize a function. So same thing, finding theta in the parameter space that minimizes the sum of KL divergences between pi and pi theta I.
So it's just the same consensus problem in terms of
Correct. So we're going to find a single theta that explains all the observations in the network in the sense of curva Leibler divergence.
The models may be different.
The models might be different, yes, but I'm going to find a single theta. Right. And this is not seen here, but now before we had learning, which is concentration of measure around single theta. Now I'm going to have consensus learning if this concentration happens for all agents. If all agents concentrate their beliefs around single theta, that is going to go consensus learning. Right. So now is the new thing. So what happens now when we have distributed optimization problems? So I'm going to propose a slightly different version of stochastic mirror descent, which I think the proper name would be the distributed stochastic entropic. Entropic because you use Kullbaum-Leibler divergence. Mirror descent. So it's going to be similar. So this part is the same, exactly the same. But now we have, this is for agent I. And agent I only observes xi. Right? And what we have here, instead of having a single KL divergence, remember, here we have the distance between the optimization variable and the previous iterate. What we have here is a weighted distance between the optimization variable and the previous iterate or previous beliefs of all my neighbors.
And this Kullbaum-Leibler divergence can be written as just a function of theta. As we, this pi is from some parameter.
Right. Yeah. And so this is the step in the stochastic mirror distributed version of stochastic mirror descent. So this is the gradient, let's say local gradient. And now the difference is that this Bregman divergence, now we have average of Bregman divergences between the random variable, between the optimization variable and the beliefs of all my neighbors. And what is even more further magic of this is this problem also has closed form solution, which is even better. And what is closed form solution is algorithm 5. So what is this? Is the belief of agent I at time k plus 1 is going to be, so first part is the same, likelihood. And now, instead of prior, I'm going to have geometric average of the priors of my neighbors. Weighted, yeah, weighted. So what Bayes' theorem says is that your posterior is likelihood times prior. And what this says is now the distributed version is your likelihood times weighted average of the priors of your neighbors. So this is natural extension of Bayes' theorem to the distributed setup. And it's shown that it's an optimal way to do it. It's a natural extension, right? So now the question is, first one, does this achieve consensus learning? And if this happens, then what is the convergence rate? So this is the two questions that we're going to solve. And we are going to explain this for many different scenarios. So what happens with the parameter is static, or when the network is static, or when the network is changed with time. What happens with the network is directed, but also what happens if the network is undirected. We prove convergence of the algorithm, and more importantly, we prove non-asymptotic convergence rates. And this is just the name of people that have worked on this problem. Yeah, so this is just a picture, just a geometric interpretation. So this is probability simplex. P is the distribution that we want to find, that we don't know. These are the members of the family of distributions, and we just want to find which one of these three is the closest to P, but we don't know P. That's the problem with that. The learning problem can be summarized like that. Right? And And this can be also used, like some of the real life application of this problem is a source localization. So you can imagine this star here as being an objective or a target. And this could be 3 sensors. But these sensors can only measure distance. So they don't know the angle where the target is located. They can only know how far is it. Maybe it's just intensity sensor or something like that. And the objective is now we have a network of sensors in order to identify the location of the target. What is the most likely position of the target? If we only have one sensor that measures distance, the only thing he can say is this is the red star here. The only thing we can say is, okay, it's within certain radius. But now, if we have multiple sensors, ideally we would like to say is here with high probability. And in here, black means the probability of being in certain space. So what you can interpretation here is you have this is the parameter space, and then you can take a grid, and each point in the grid is one possible parameter theta. So you will assign high probability or high beliefs to the thetas here, and that's the one real life application of this.
Is it possible to use Wasserstein distance?
Yeah, it would, but the thing is, I don't know if you replace Wasserstein distance there, you will have closed form solution of the iteration.
I mean, for this application that you showed with the system of sensors, if we just use Wasserstein distance to average these distributions.
Yeah, I think we will need to see what happens. But the interesting here is that when you have KL divergence, you have closed form, so you don't need to compute anything. You already have the algorithm. Just plug and play. It's very good.
As far as I know, you have a paper with Gasnik and Skip on Wasserstein barycenters, but there the probability measures I consider to be discrete.
Yeah, these are discrete probability measures as well. Yeah.
And in the example you just provided, it seems like they may be.
Yeah, so I have the results for continuous probability distributions, but here I'm just, for simplicity, I'm presenting just the discrete version, yes. Because the continuous one, it gets very messy with the mathematics, and then you forget about the original problem because it gets very complicated. So there is these 3 results that I'm going to show. What is the convergence rate for when the graph is changing with time but undirected? What is the convergence rate when the graph is changing with time and directed? And what happens with static graph? What is the optimal convergence rate for when the graph is static? So these are the 3 algorithms. So original one works for time varying undirected graphs. This you can consider as primal approach, right? Because it doesn't matter if the graph is changing with time, as long as it's undirected. But if the graph is directed, you need to change something else. And this is maybe something I will present Thursday or Friday, I don't know. Which is how can you deal with directed graphs? This is at this moment it's not important to understand why this looks like this, but let's say we have the algorithm for that. And the general theorem that I'm going to present is as follows. So these are the beliefs of agent I. So all the theorems are going to say the following. Under appropriate assumptions, which I'm ignoring for the moment, the group of agents that follow each of the algorithms that I showed you before, there exists a time n such that after this time n, with probability 1 minus rho, for all k bigger than this n, so all these k iterations, the beliefs on the wrong hypothesis, on the non-optimal ones, are going to decay exponentially fast with parameter gamma 2 and gamma 1. Is this formulation clear? So you need to wait a time n such that after this time, your beliefs on the wrong hypothesis go to 0 exponentially fast with parameters gamma 2 and gamma 1. And of course, now the obvious question is, okay, what is n, what is gamma 2, and what is gamma 1? So what I'm going to show next is for the 3 cases that I show you, what are these 3 values? And this is the main table.
So is it like about the situation? I mean, if you consider hypothesis testing Cesar, you say that after some point the probability that we are going to reject the null hypothesis
decay to 0 exponentially fast, yeah.
Indicates if it is like not true. There's no hypothesis.
Yeah, so this is the distributed extension of hypothesis testing. So, right? So let's see what are these values. So remember, n is the time you need to wait. And for all the cases, so graph is time varying undirected, time varying directed, or fixed. Metropolis is just one particular way to choose the weights. I think you show them in your slides. It's when you have self-weights like 1 over the maximum between the degrees. This is called the metropolis. And regular directed graph is when in directed graphs, you might have different number of in neighbors and out neighbors. So regular directed graphs is when this number is the same. Same number of in and out neighbors. So for all these cases, n does not change. In all cases, the time you need to wait before exponential decay is log 1 over rho. And remember, rho is the one that says this happens with probability 1 over rho, 1 minus rho. So if you want this to happen with high probability, you choose rho to be very close to 0. But the closer to 0, then the bigger the n. So this is the trade-off. If you want something to happen with high probability, then you need to wait longer. Now, remember the rate of convergence here, gamma 2, is also the same for all the cases. So basically, it does not matter what type of graph do you have. Convergence rate is always the same. It's some constant value. And what changes here is gamma 1. So gamma 1 is also like a little delay that you need to wait before this number pops, kicks in, right? So for the case of you have fixed undirected graphs, this is gamma 1 is like ON. When you have time varying undirected graphs, you have n squared over eta, and eta is just another parameter. That can be, for example, 1 over n. So this becomes n cubed. But if you have metropolis weights, this comes back to n squared. If you have regular graphs, you have n cubed. But the worst case is when you have graphs that change with time and they are directed. As of now, the only result that we have is that the worst case is n to the power of n. So you can imagine that for slightly bigger graphs, this is already untractable. So you can imagine a small graph of 10 agents. So this is 10 to the power of 10. So now plug here 10 to the power of 10. So this k should be of the order 10 to the power of 10 before it becomes more negative than this value. So it's this bound is pretty much useless in worst case.
Pessimistic.
It's pessimistic, yes. But this is worst case, right? So this is the table for, you see, the difference between this problem and the problems we studied with you and with Sasha is that here we have large classes of networks. With this primal dual analysis, we only have fixed static graphs. And we already know this dependency is number of nodes. This is our result, right? Square root of condition number of graph Laplacian. But ideally, we would like to have same results, but for all these classes of graphs. And this is what is missing, like having all these type of results for this primal dual analysis. So this is just simulations. And then, so the question is, okay, this is very bad, right? So what is the worst graph? You know, in the same way that nested-of proofs lower bound by having a very bad function to optimize, the question is, what is the graph for which you achieve n to the power of n? And that will show that your upper bound is tight, right? You cannot go worse than this. And this is an open question. As of now, we don't know what graph will achieve this bound, which might indicate that this may be too pessimistic. As of now, the only bad graph that we have is this one, and this graph was invented by Alex Olszewski, like my PhD advisor. I show you already this in my talk. So it's a very simple graph. It's not changing with time, but it's directed. So this node talks to this one talks to this one, and so on, and all of them goes to the first one, and now we have these two last nodes talking to each other. That's the only thing we have. And the result is the following. So number of nodes versus number of iterations that you require to be epsilon close to optimal solution. So this grows exponentially with the number of nodes, which means that for this graph, the bound is e to the n, not n to the n. It's a little bit better, but just a little bit, right? So that's I'm just going to, so this is, so we have the general case. What I showed you before is for the case of theta being finite probability space, so finite number of hypotheses. But I also have the result for when theta is a compact subset of RD. I'm not going to explain it because it's too complicated, but the result is sort of the same. So the beliefs on a ball of radius r is bigger than 1 minus something that decays exponentially fast with probability 1 minus sigma. Right? You can see sort of that. And this is a ball where the optimal parameter is located. So what this is saying is you fix a ball R, and the beliefs in this ball around optimal parameter is going to be very close to 1 when k is very large, so because this goes to 0. So that's so what this explains is just need to do a lot more mathematics to prove exactly the same result, but it's the same. Yeah. And what is interesting here is, okay, I prove general case for any sort of two probability distributions, and then what happens, they say, when the probabilities are Gaussians. So optimal probability distribution is Gaussian, my family is Gaussian. It turns out that you can rewrite this in this optimization problem. Then the algorithm that I propose, like when you plug the Gaussian densities, just translates into these two equations. So this is the algorithm. This is not a new algorithm. This is just, I took the algorithm that I proposed, and I plug Gaussian distributions into B, into the mu's, and all of that. And then just turns out to be this type of thing. You can do, okay, what happens if you know the mean, but you want to estimate the variance, so the opposite. This one is you know the mean, you know the variance, and you want to estimate the mean. If you know the mean and want to estimate the variance, you do exactly the same, and then the algorithm changes a little bit. And what happens if now you have Poisson distributions, exactly the same, you get a new algorithm. And what happens when you want to estimate mean and variance at the same time, you get another algorithm. So what is interesting here is because we understood the estimation problem from optimization perspective, we proposed a general algorithm, and now here for every probability distribution that you want, you just need to plug it, and then they will give you suddenly the best thing you can do for the distributed optimization problem. And the theorem is also general, so we also know convergence rate of these, dependency of the graph structure, so it's the same. Right? So this is the main result. So the problem of distributed estimation, so we start from variational interpretation of Bayes' theorem, and we propose a set of new algorithms with probable performance, and we show also non-asymptotic rates for concentration around the correct hypothesis. And there is questions. There are a couple of things that are interesting that I'm not going to talk about, which is relationship with the linear regression and Kalman filtering. And this is a very interesting topic here, because you can express Kalman filtering as Bayesian procedure. So if we follow the same interpretation, what this says is that now we can propose distributed Kalman filter by following the same ideas. And this is something that it would be very nice. I started working, but I never finished it. But I think it's right there. It's within reachable distance. Yeah, I think that's it. Yeah.
Questions? Yeah. I wanted to ask about the initial setup. Did you assume that the parameter, that the dimension of the parameter space is 1, or it can be used for any dimension?
I assume the parameter space is there is finite number of members in the parameter space. So in that case, dimension does not matter too much, because I have finite number of them. Right? Let's say
finite number of candidates.
Right, because you can interpret. Let's say, okay, I have very high dimension. I have dimension 1 million, but my family only have two thetas. Let's say one vector of dimension 1 million and another vector of dimension 1 million. I care only about theta 1, theta 2, not the dimension of what they interpret. Yeah.
Okay, so you are just choosing, and this applies to this stochastic mirror descent. Okay, because I wanted to know. I mean, if this stochastic mirror descent could be applied for solving like general Bayesian inference problems with approximating the posterior distribution, because nowadays, as far as I know, some EM algorithm is used, and this one cannot be applied directly for this problem.
Maybe this is a way to understand this problem. I just haven't explored it. Yeah, that might be a good thing to see. How can you? Yeah, because usually these Bayesian posteriors are used to approximate. You use these to approximate posteriors. Right? Maybe this is a good way to do it. I did it for different motivations, so I guess it would be a good thing to explore. Yeah.
Because there is really part of science.
Yeah, and what is more interesting is we have distributed interpretation of the problem. So for any problem that you have in centralized case, if you follow this path, then you will have distributed version. So if you have any estimation problem, then you get distributed one, and then you can propose maybe distributed EM algorithm would be a good way. Like in this way, right? The same way as distributed Kalman filter. Maybe I have one slide here. Yeah, so I never finish it, but basically you can write Kalman filter as these two steps. Prediction step, which is on expectation, and update step, which looks very similar, right? It's exactly, this is centralized Kalman filter.
And probably the second term, the Kyle divergence, shouldn't there be k and not k plus 1?
No, because k plus 1 here is from the prediction. Because now we have prediction, so this is the new thing with the Kalman. So after looking at this and hearing on my talk, what is the next obvious thing to do here? The same thing we did in the talk. I changed this KL divergence by weighted KL divergence from my neighbors. And we know this has closed form solution. And we know the distributed version also has closed form solution. So by looking at this and writing distributed version, then we have exactly distributed version of Kalman filter. So this is like an easy way, like immediate way to propose distributed version of common filter. But this is just the idea. You have to like work it out. But this is the, I think it follows from this slide. Yeah.
And do you think about any other algorithms apart from the stochastic mirror descent?
Yeah.
Maybe acceleration of this method.
So that's another open question for this problem, which is okay, in the same way that you can prove, let's say, a little bit of acceleration for stochastic gradient descent and mirror descent. So can we propose what would be the accelerated version of this algorithm? That would be a very nice paper to have as well.
And are there any results for directed static graphs?
It follows the same in the same category of directed time varying. Yeah. Because this worst case is for static graph. Yeah. Another interesting direction is in what is called efficient communication. So right now we assume two agents can talk to each other. They send beliefs, right? So they send a whole probability distribution to their neighbors. So a paper that I think it would be very accessible to write is what happens if you only send samples from your beliefs. Right? I have mu, I sample from mu, and that's the number I send you. So I don't have to send, because this is the case when, let's say, parameter space is finite but very large. Let's say it's size 1 million. So communication will mean that I have to send you a vector of size 1 million. But because this is a probability distribution, most of these values are going to be 0. So I can, for example, take a sample from mu and only send you this value. So efficient communication there.
Every agent has, so he sends not only the parameter, but he has like some prior of this parameter, and he can sample from this prior and send it.
Right. So mu is a distribution over the probability space. So I can sample and send you like theta 1 or theta 2, just the output of this sample. So that's another paper there. And there is a recent paper from NIPS last year by Sebastian Stich, was a former postdoc of Nesterov. And he has this paper about distributed optimization with sparse communication. So I think if you take this paper and this and merge them together, you will have the new result there. That is another work that I think can be done rather easily. There's many things to do here.
Actually, there are papers on sparse communication because what you said about sampling from mu is pretty the same.
Yeah. I think just a mixing of the things, because remember that we're doing geometric average of distributions. So I think the key would be understanding how do you define geometric average when you only have samples from the distributions. So that would be the case. And I think that's it. Yeah, I don't think I have... yeah, right. This is what I was telling you. So what's the obvious way to write distributed common filter? This is local prediction and then distributed update. And okay, that's it. Yeah. Yeah.
Do I get it right that it is possible to use the method that you described? You described a number of examples for conjugate distributions.
Right.
And is it possible to use it for non-conjugate distributions?
So as of now, only conjugate distributions. Because why? Because they're conjugate, so mu is going to be of the same family as the prior, so you always belong. And also geometric average, weighted geometric average of members of the exponential family are close, so the geometric average is going to be some distribution in the same family. So you always remain, so you only need to keep track of parameters, not the shape. But another line of work here is same problem, but with non-parametric distributions. Right, that's a whole new area to explore. So zero works in that area, so that's another thing to explore. Yeah.